All right, we are moving on to chapter 12. This one is integration. So we've done all of your partial derivatives and your derivatives with multiple variables, and now we're going to do integrals. And this is my favorite chapter of the four that we go through. I like this one the best. So I guess once you're like a math nerd like me, you get to decide if you prefer integrals or derivatives. I'm kind of partial to integrals. No pun intended, but now I just made a funny joke. So, oh boy, we better get started here. Okay, so we're going to back up to when you first learned about Riemann sums in Calc 1 again. It's always nice to relate this to what you first learned in easier terms. So recall Riemann sums for integrals. I should give extra credit if you guys catch jokes or something, but they would just be awful jokes, so I don't know. Okay, so we have a function. I usually make these videos at the end of the week when I'm in a good mood, so maybe I just get a little bit punchy. Okay, that's such an old lady term. A to B. Oh boy. And let's call this guy f of x. Okay, and let's say we wanted the area under that curve there. It's an A. Okay, so remember when we first did this, we thought about infinite rectangles. Okay, infinite rectangles where the base of each rectangle would be b minus a over n, where n was a large number and eventually like n approached infinity, if you remember that. Okay, and we might have also called that delta x. Okay, and then we had the height of those rectangles was your function evaluated at some x value. Okay, it might have been left, your left endpoint. Then xi star would have been that initial a plus how many delta x's would get you to the next one. But starting with I is 1, so at first you don't hit any delta x's. Okay, you're just at the left endpoint, and then you had one delta x and another delta x. We also had the right endpoints, where xi star would have been a plus delta x times I. And then we could even have the midpoint. Remember, we did those two where we averaged. Let's see, xi star would have been, oops, I guess there's a few ways we could have done this. Let's see, a plus delta x I minus 1 plus delta x I over 2. Yeah, because it would depend. Sorry, I was just thinking in my head there. So that could simplify down to a plus delta xi minus delta x over 2. There are different ways to express it, but it doesn't really even matter because it didn't really matter if we were thinking about left or right once we took the limit. Okay, and then let me just get this graphically in here. So we would have a base that would be delta x, and then a height, and again, it would depend, f of xi star, depending on where you were taking that x value, left endpoint, right endpoint, midpoint. And we have that subscript I because there's multiple f of x's, right? There's the first one, the second one, the third one, the fourth one, and on and on and on to the infinite one. Okay, and so then you remember that we talked about, well, let's take all of those, you know, where n is a really big number, take all of those areas of the triangles and add them up. Okay, and even better, here that would be an approximation, right? Even better is if we could do the limit of that as delta x just approaches 0, okay, of I equals 1 to the n f of xi, star, delta x. Okay, and if delta x is approaching 0, then n is approaching infinity. Okay, so it's kind of the same way to think about that too. And then we said, well, ta-da, that's an integral. The integral from a to b of f of x dx. Okay. So hopefully you remember that. Nice little flashback to Calc 1. And of course, we're going to add just a little something to it to make it apply to Calc 3. Okay, so now we're adding another dimension. So we're not thinking about area. Now we're thinking about volume. So we're not adding up infinite areas of rectangles. We're adding up infinite volumes of rectangular prisms. Okay, so let me do my best to do a little drawing here. Okay, so this is your x, your y, your z. Okay, and then we'll have your x's from A to B. Okay, so it's kind of like a side view of what we just had, right? But your y's also go from C to D. Okay, so we've got this region down below, and we're taking the integral to get the volume that's above it under a certain surface. So before we were taking the integral over a range to get the area under a curve. Now we're taking the integral over both of these ranges to get the volume under the surface. So let me kind of draw in a surface here. We have some like 3D surface going on up here. And so this would be like your f of x, y, right? Your z. And we could think about like some rectangles down here. Maybe there's a little rectangular prism here. Okay, and where this is like the height of it is on the surface. Okay, and then maybe we've got another one over here. Okay, so we would want infinite rectangular prisms. Okay, well, we know that the volume of a rectangular prism is length times width times height. Okay, so our length and our width, right? That would be our delta x, which would be b minus a over, they're going to call it in your book m. Okay, I think they do actually. It doesn't really matter if you call it m or n. And then your delta y will be d minus c over n. Okay, so we could, just like we're splitting, again, back in the Calc 1 example, just like we're dividing it up into equal intervals, we're going to divide this up into like equal rectangles. Okay, and then the height will be f of some xi star, yi star. Okay, so the volume of 1, and again, those xi stars, yi stars, now we have to be a little bit more specific, right? Are we taking like the left endpoint for the x's and the right endpoint for the y's? Are we doing some midpoints there? You got to pay attention there because there's many spots in that base that those xi stars could occur. Maybe it's that corner on every single one. Okay, maybe it's the middle on every single one. All right, and again, it's not really going to matter because we're going to take a limit, but the volume of one rectangular prism would be delta x times delta y times the height. Okay, so the volume of all. Okay, and I should do, again, these are kind of approximations. So our summation, okay, we're going to do a double summation from I equals 1 to m, and then j equals 1 to n of f xi star. Okay, right? So the x's go from 1 to m. yi, or yj star. In fact, I should have made all of those those should be j's, because it's not necessarily the same value there. Okay, you could be looking at like the first x and then the like the third y. Okay, that index doesn't have to be the same, but you'll get the height, and then delta x, delta y, which sometimes we just write delta a. Okay. All right, so you kind of, that's just showing that you would add up the volume of all of those rectangular prisms. Okay, so what we're getting at is the volume would actually equal the limit as delta x and delta y approach 0 of that summation, which is your integral from a to b and from c to d of f xy dy dx. Okay, and we're going to learn a theorem here in a little bit. It's called Fubini's theorem, that says that that's equivalent to c to d, a to b, dx dy. Okay, so just like when you were in Calc 1, we're going to start with doing this geometrically, and then we're going to jump to the actual integrals. Okay, I would guess, I don't want to get too far ahead of myself here, that like I could stop the video now and you guys could probably do a lot of these examples that I'm going to do. So this is one section where I would strongly encourage you to pause and try it yourself. That's how you're going to pick it up the easiest. Okay. Don't get lazy on this one. This is a good opportunity to get a nice start to a chapter and really understand this first section. Okay. So we're going to do some examples, and all of the examples that I've chosen are even problems in the book. Just to kind of mix it up a little bit so you get something beyond just the examples that are in the book. So our first example is that we have this region R, which this notation is showing that we go from 0 to 4 in the x's and -1 to 2 in the y's. Okay, it's kind of the same as saying, let me get the... You might see it written like this too. Okay, so that's two different notations for the same thing. Use a Riemann sum with m equals 2. So remember, m is how many intervals we divide the x's into, and n equals 3, to estimate your integral over r of 1 minus xy squared dA. Okay, and remember, this could also be written as your integral from 0 to 4, -1 to 2 of 1 minus xy squared. We've got the y's on the inside here, so we put the y dy here. These are y values, these are x values, so then we put dx. Okay, or we could do the integral from -1 to 2, 0 to 4, 1 minus xy squared dx dy. Okay, so we're just getting into a bunch of different notations here. So, and it also says to use your upper left corners. Okay, so probably the easiest way to do this is to kind of organize your work on a graph. Just the xy plane. Okay, so your x's go from 0 to 4, and we're going to divide it into 2. So we're going to have 0, 2, 4. Okay, and then your y's, we are going to have from -1 to 2. And we're supposed to divide it into 3 sections. So -1, 0, 1, 2. Okay, so you can see we kind of made this grid here that's going to help us organize our work. And in fact, I'm going to kind of outline. Okay, so we have the points 0, -1, 2, -1, 4, -1. Okay, sorry. 0, 0, 0, 1, oops, 0, 2. And we've got 2, 2. And here we've got 4, 2. I'm going around the perimeter first here. 4, 1, 4, 0. And then on the inside here, let's see, we've got 2, 0, and 2, 1. Okay, so you have to think about that there'd be a surface above this. So think about like your rectangular prisms coming out of the screen. And make sure too, we only need to do the upper left corners. So we will be estimating the rectangular prism with this base using the height that we get from that corner. Okay, so this corner would go with that base, this corner would go with that base, this corner, this corner, this corner. Okay. All right. So we can also get that the area of each of those is 2 by 1. Okay, so all of the heights we just need to multiply by 2. Okay, so your dA or your delta A is 2. Okay, so we're going to find f of 0, 0. Again, using our function there, so it'd be 1. We'll find f of 2, 0, which would be negative, or it'd be 1. Did I mess this up a little bit? No, I don't think I did. I think I messed it up in my notes. Right, that would be 2, 0 would be the upper left. Just a second. Yeah, I think I messed it up in my notes actually. Okay, we're good. So let me know if you're watching the video and you think that I made a mistake there, let me know. But 2, 0 would also be 1. Okay, and then f of, let's see, 0, 1 would also be 1. We're going to have a lot of 1s, right, because of that 0. F of, let's see, 0, 0, 2, 0, 2, 1 would be -1, right? Because x is 2, y is 1, that makes sense. F of 0, 2 would be 1. And then f of 2, 2, we'd have 1 minus 8, so it'd be -7. Okay, let me just make sure I didn't make any mistakes, because like I said, I'm looking at my notes here, and I've got different answers. But I think I'm okay. All right, so we would do, that's the height of each of those 6 rectangular prisms. So we multiply each of them by 2. So we can also just do 2 times the sum of those. 1 plus 1 plus 1. Right, my 1's weird. Plus -1 plus 1 minus 7. So we're going to have 2 times, is it -4? Yeah, so we'll get -8 as our estimate for that integral. Okay. All right. So one thing that you could do is come back and do this one as a practice problem once you learn how to actually calculate that integral and see how close you get to -8. Probably won't be all that close, but I don't know. I haven't tried it yet. Okay. There you go. So let's do another example here. In this example, they give you the integral, and they ask you to interpret it as a solid. Okay. So they give you that, and then they give you the region. Okay. So they want you to draw it. Draw this three-dimensional region here. So what we can do now is figure out that rectangular base. Eventually we're going to move beyond rectangular bases, but for now, this is what we got. So x goes from 0 to 5. Okay, so x from 0 to 5. And y goes from 0 to 3. So this would be our base. Okay, and then this function gives us the height. Okay, so when x is 5, we have a height of 0. Notice it doesn't depend on y at all. It's linear. Okay, z equals 5 minus x. Okay, so in the xz plane, we just have a line, right? When x is 5, z is 0. When x is 0, z is 5. This is what it would look like in that plane. Okay, so then I'm going to test your skills on drawing here. Okay, it looks like that. It's like a little wedge. Okay, which again, we can, if you guys remember when you were in, little side note here, when you were in Calc 1, one of the things that they did right off the bat was they gave you some geometric shapes here. Like it was, I don't know. They'd give you, here's a line, here's a quarter of a circle. Find the integral from A to B. And use geometry to do it. Okay, so same thing, we can use geometry to find this. It's a triangular prism. Okay, so the base here would be 5 by 3 times 1/2. So the area of the base would be 1/2. I'm sorry, I already have the 1/2 there. 1/2 times 5 times 3. Okay, there's your area of the base. And then the height of the whole thing is 5. Okay, so we'd have 1/2 of 75. Okay, or 37.5. Okay. All right. Okay. Now, I know you guys are just dying to get into the actual integrating here. So I'm going to give you one. The integral from 0 to 1, 1 to 2, 4x cubed minus 9x squared y squared dy dx. Okay. I'm going to challenge you right now to go ahead and pause the video and do what you think you're supposed to do. I'm going to bet you could figure it out without me. Okay. All right. Now, if you're still listening, I hope that means that you were just paused for a few minutes. Okay. So the way we do this is we go from the inside out. Okay. We're going to integrate with respect to y, treating x as a constant. So think about this, and I'm just going to leave the 0 to 1 out here. Okay, so if 4x cubed, that's a constant. If we're integrating it, then we have 4x cubed y. Okay, now we're integrating a y squared term, so we're going to bump it up to a y cubed and then divide by 3. Okay, so we'll have 9x squared y cubed over 3. And we are going to evaluate that from y equals 1 to y equals 2. This is one way that you can write that. You can also write y equals 1 and y equals 2. Sometimes that's nice when you have a lot of variables that you're working with. Okay, so now we're going to plug in. We're going to have 8x cubed. Let's see, I'm going to cancel that out to make it a 3. Minus 24x squared. When I plug in the 2, and then when I plug in the 1, I'm going to have 4x cubed minus 3x squared dx. Okay, and that's an integral I can do, right? I'll simplify it first. Combine my like terms. 8x cubed minus 4x cubed, so I got 4x cubed. Negative 24x squared plus 3x squared, so minus 21x squared dx. And we got that, right? So we're going to have x to the 4th minus 7x cubed, evaluated from 0 to 1. So I'll have 1 minus 7 minus 0 minus 0. So negative 6 for an answer there. Okay. As I mentioned before, we have Fubini's theorem that says this is the same as the integral from 1 to 2, integral from 0 to 1 of the same expression, integrating with x first. Okay, for this problem, it doesn't make much of a difference. Doing that won't necessarily simplify it. You will run into problems where that first order doesn't work at all, okay? And you have to switch it to get the second order. So if we were doing this, let's see here, we would have 4x to the 4th over 4, so x to the 4th, minus 9x cubed y squared over 3, so 3x cubed y squared. And we'd evaluate that from x equals 0 to x equals 1. And then take our integral with respect to y. So this would be the integral from 1 to 2 of, let's see here, we'd have 1 minus 3 y squared and then minus 0. Okay, and so then we'd integrate that, and we'd have y minus 3y squared over 3. So just y minus, or 3y cubed over 3, y cubed, evaluated from 1 to 2. So then we'd have 2 minus 8 minus 1 minus 1, and we get our negative 6 again. Okay, so again, if you want to rearrange it like that, you can. Okay. At this point, if you haven't, I would go back and check our estimate up here on this guy. Right, now you know how to do this. Then go back and see how close you get to negative 8. I don't know. I haven't done it yet. Okay. A couple properties then that show up at the end. One of them is pretty handy. A lot of them are pretty intuitive. Your integral over r of g of x times h of y. In other words, if it's separable, if you can get the x pieces times the y pieces, that is kind of a nice little shortcut because we can take your integral from a to b. Oh, and this is assuming r is ab by cd. Okay, so you could do the integral from a to b of your x part times your integral from c to d of your y part. Okay, so an example of that, if you have your integral from 0 to 2, integral from 0 to 4 of y cubed e to the 2x dy dx. Okay, again, I'm going to encourage you to stop the video and do that without using the property. Okay, don't use this yet. Just how I just showed you, integrate with respect to y, then integrate with respect to x, and see what you get. Okay, so pause, and welcome back. Okay, so the other thing we can do is this is separable. So we can rewrite this as your integral. Let's see, the 0 to 2 goes with the x. So integral from 0 to 2 of e to the 2x dx, and multiply that by your integral from 0 to 4 of y cubed dy. Okay, and that's going to be much easier. So your integral of e to the 2x would be 1/2 e to the 2x from 0 to 2. And then we'll do y to the 4th over 4 from 0 to 4. So we get 1/2 e to the 4th minus 1/2. And then we're going to multiply it by, let's see, 64, right? 4 to the 4th power over 4 be 4 to the 3rd power, which is 64, minus 0. Okay, so e to the 4th minus 1 over 2 times 64, we're going to get 32 e to the 4th minus 1. And that should be equivalent to what you got when you did it the other way. Okay, there are some more pretty obvious properties that are at the end of the chapter for you to take a look at. Integral over r of f of x, y plus g of x, y dA. We can separate that. We generally wouldn't, we just kind of, we didn't up here. When we did like this one, we could do your double integral of 4x cubed and then subtract the double integral of 9x squared y squared. You could. There's not much of a reason to do it. It's more likely you go the other way, right? Your integral, if you have a constant out front, you know what you can do with that, and it's a good idea. Take that constant out front, just like single integrals. And this one is kind of a weird one that makes sense. If f of xy is always greater than or equal to g of xy, okay, then your double integral over r of f of xy will always be greater than or equal to your double integral over r of g of xy. Okay, that should make sense. If one surface is always above another surface, then the volume below it should always be higher than the volume below the other surface. Okay, that's it. So that was kind of a nice little section here to get you started. I think you're going to do a nice job with it. So good luck.